Behind me dips eternity. Before me immortality. Myself the term between. Death but the drift of eastern ray, dissolving into dawn away, before the west begins. 'Tis kingdoms afterward the same, in perfect pauseless monarchy, whose prince is the son of none, himself disdainless dynasty, himself diversified, in duplicate divine. 'Tis a miracle before me, then 'tis a miracle behind, between, a crescent in the sea, with midnight to the north of her, at midnight to the south of her, and maelstrom in the sky.
Good afternoon. You're tuned in to Weltanschauung, broadcasting from deep in the heart of the Petro Metro, aka Houston, Texas. I'm Mike DeLeonardis, bringing you news and analysis of science, technology, and the human condition. And for today's show, we're going to dive into the mechanics of black holes to see if they can shed some light on the origins of space and time. While some may still cling to the idea that by 1900 it was thought that the major laws of physics had all been discovered, that was proven wrong by 1915 when Einstein extended Newton's theory of gravity with his theory of general relativity, which was soon followed by quantum mechanics, which revolutionized much of our understanding of the nanoscopic world and is the backdrop behind the functionality of all our high-tech gadgets. Quantum mechanics describing the atomic and subatomic realms using particles and wave functions that ultimately united three of the fundamental forces of nature, electromagnetism with the strong and weak nuclear forces, while general relativity painted a large-scale picture of the universe whereby gravity is the curvature of space-time caused by the presence of mass and energy. Although both theories have demonstrated extremely high fidelity under intense scrutiny over the years, so far all attempts to unite the two into a grand theory of everything have come up short. Many schemes have evolved to tackle this conundrum, most famously string theory, but other theories such as loop quantum gravity are also paving the way toward that end. That said, as we delve into the nature of space, matter, and time, we're going to need some expert guidance to bring us closer to understanding the nature of the universe. And to help me figure out which way is up, my guest today is Dr. Stefan Gielen, a professor of theoretical physics in the School of Mathematics and Physical Sciences at the University of Sheffield, who specializes in gravitation and cosmology, and who recently published a paper stipulating that rather than being endings, black holes may transition into new beginnings. Welcome, Dr. Gielen.
Nice to talk to you today.
Let's just go right out of the chute. And at the end, we're going to probably talk about unification. But the two differences or the two major theories are some are extra dimensional, like string theory. That's the big one. That's the popular one. And there are other theories. I'm thinking of loop quantum gravity. I didn't want to accuse you of being under that umbrella, but those are the two big ones that I think of when I think of the unification of quantum mechanics with general relativity. And so I guess we could back up and just do a little bit of differentiation between the two.
Yeah, sure, absolutely. So the goal is to combine quantum theory with general relativity in some consistent framework, where general relativity is our theory of gravity according to Einstein, which is a theory of space-time, dynamical space-time. Quantum theory is what we need to describe atoms, elementary particles, very small things, right? And the two have very different principles. So we need to somehow find a unifying framework that's built on these principles. And the different approaches, I guess, they disagree a bit on just where they start, right? So you could take quantum mechanics as fundamental in a given prescription and then try and fit gravity into it. Or you come from the other side and you say, general relativity, this is kind of sacred. How can you fit quantum mechanics into it? So this is a bit where the differences start. More practically, you already mentioned the dimensions. That's a very important difference. So the string theories are typically defined in a certain number of dimensions where they're consistent, typically 10 or 11 dimensions. And indeed in loop quantum gravity, because you have different starting points, it's a different type of quantum theory. The idea is to have 3 dimensions of space and 1 dimension of time.
Okay. Well, now that we got that out of the way, since you're an expert in gravitation and cosmology, gravity. Okay. I guess it's the curvature of space-time shaped by matter and energy. But that's my kind of like knockoff, answer to that. But I read somewhere in doing some research for this discussion that gravity is not really a force. Is that true?
Yeah, so that's basically the picture that we get from Einstein. It's not a force. It has to do with the curvature of space-time, right? So if you're attracted to, a star or black hole or something that's very massive, it's not because you're pulled towards that object by force. It's because space and time are actually curved, right? So you're not going in a straight line anymore. You're kind of following that kind of bend because the space and time around you are actually curved by the presence of that object. So it's very different picture. So when we do some like outreach for the general public, there's always this nice way of illustrating this with like a rubber sheet, right? So you have your rubber sheet, you put something that's very massive, right? And then you see that the rubber sheet is kind of curved by that. And then you have a small object that's trying to go past. It's not going to go on a straight line anymore, right? If you imagine that. So that's a very nice analogy. This is basically, but of course it's very abstract. It's very mathematical, right? Space and time being curved, you have to somehow accept that.
Right.
But that's basically what happens. Yeah.
I guess that's how orbits happen and all of that when objects attract one another. One orbits, like say the moon is orbiting the Earth and the Earth is orbiting the sun. Mm-hmm. And, this is very interesting. Very interesting. It's almost like a Ferris wheel in a sense. And I'm getting towards black holes because you've got this big old black hole at the center of our galaxy, Sagittarius A, Sag A. And I'm thinking, is it a good analogy to think that, okay, so this black hole, it at the center is the singularity, and let's say that's hopefully, supposedly that's where time stops, and that's like the
exactly.
the axis of the Ferris wheel, and I don't know, it seems like the black hole is like an axis spinning the galaxy around. Is that pretty good? Is that decent enough?
Yeah. So that's what it looks like from the outside, right? So you see that the fascinating thing about black holes is that they're curving space and time so much, right? That basically once you're inside, so there's this, surface that's called the event horizon, which is basically the point of no return, right? So if you're an observer, if you're some object that falls into the black hole, once you're beyond the event horizon, you can't get out anymore. And the way to understand that is basically that the roles of space and time are reversed once you're inside the black hole, right? So from the outside, it looks like this is some object, some very compact object that's somewhere in space, right? Once you're inside, it's basically like you're somewhere else in time, right? And so then you're falling towards what you already described, which is a singularity. You're falling towards a singularity, which again, from the outside, you would say that's the center of the black hole, right? It's just a point in the middle. But when you're inside the black hole, this is now time, right? So time kind of moves into the singularity. I don't know if that makes a lot of sense, but that's basically what happens, because the curvature of its space and time is so extreme that basically the roles of space and time are reversed. And in a sense, that's why you can't get out anymore, because trying to get out would be like going backwards in time, which you can't do. That's impossible, right? So you can only move forward in time. You can't go backward, which means that inside the black hole, you can only keep falling in towards the center. You can never go back out.
Okay, I'm listening to what you're saying, but I guess it'll take quite a bit of meditation and maybe some medication along with that to let that sink in. But I'll just leave that at that there. Time and space are reversed inside a black hole. Very interesting.
Mm-hmm.
Before we go on to that, well, okay, there's this problem I've got reading the paper, and I'm just going to use the term black hole, white hole duality. That is, you enter a black hole and get spit out by a white hole. But this term singularity seems to be some sort of problem there. Of course, you can't have an infinitely. It doesn't make sense. When you get to a true singularity, that's infinity, and that screws everything up.
Exactly.
So, what sort of scales are we looking at when we think of the center of the black hole? And I'm just going to guess that, is it the Planck length, or what sort of very tiny, I'm assuming very tiny spaces?
So, right. So, I mean, if we're talking about Einstein's theory of general relativity, everything is, in a sense, smooth and continuous all the way down towards the center of the black hole. But then it all blows up, as you said. Basically, everything becomes infinite. So you can think about, if you're thinking about all the energy in the black hole, it's basically just concentrated in one point, which is in the center. So all the energy is just in one point. And that's, as you said, that's kind of an infinity that doesn't really make sense. And now, when you're falling towards the singularity, of course, you will be experiencing some forces, some gravitational, which looks to you like gravitational forces that are basically pulling you apart in different directions. We usually say you get spaghettified. So that's the technical term. You get pulled apart by these forces. And again, all these forces just become stronger and stronger and stronger. They go all the way to infinity. So if we're just in Einstein's theory, there isn't really a minimal length. There isn't really a smaller scale. It's all just continuous. It just keeps growing and growing and growing and growing. But when you add quantum mechanics, then of course you expect some minimum scale, right? Because, for example, if you're thinking of atoms, your hydrogen atom has a particular radius, which you can measure in the lab, which is fixed by quantum mechanics, right? So quantum mechanics tells you that these objects have some finite size and not just points. And that's when we start talking about the Planck length. So this is a concept that comes from the quantum theory, once we start putting in the quantum theory.
Is it the Planck length? Is that what you're working with?
So, so in this model that we have, there isn't really a Planck length because it's a simple model. There's 3 parameters which you associate to the quantumness.
Okay.
And depending on how you choose these parameters, you can get the Planck length if you want, or some other length. The Planck length is more just, if you take together the fundamental constants of nature, you take your Newton's constant, speed of light, and so on. All these things are like fundamental constants. You can combine them in a unique way to get like a length scale. right? And that's the Planck length. So this is just assuming that, all these fundamental constants of nature are relevant. That's what you come up with, basically.
Okay. Well, so what happens when a black hole changes or transitions into a white hole? Yeah, that's what's going on there.
Great. So you need quantum theory for that, right? So in the classical theory, as I said, once you're inside the black hole, basically falling towards the center is like moving forward in time, but it only takes you a finite amount of time. Eventually you hit the center, and that's basically where time ends. So this is, in that sense, time comes to an end. Any object will kind of hit this boundary in a sense, which is the singularity. So the theory breaks down, and you need to do something to fix that. Now, what we did in our work was to use fundamental principles of quantum mechanics, which are based on the idea of unitarity. So that's a very important idea. So unitarity is connected to time evolution of quantum systems. It basically means that you've prepared some quantum system in your lab, and you want to evolve it in time. And quantum theory should tell you what happens at some future time. And that's a very fundamental idea. And that kind of tells you that, a quantum system can't just stop to exist. I mean, it has to evolve into something else. So in a sense, this kind of sudden singularity is sort of ruled out by this principle. So when you put that into the description of the black hole, you do end up with this kind of future evolution where sort of quantum theory comes in, and the whole thing makes what we call a transition. So this is kind of quantumness. Everything starts sort of being undetermined, right? If you're thinking of a Schrödinger cat, it's kind of a black hole and a white hole at the same time for a while, and eventually it comes out as a white hole. So this is something that happens to the future, basically, of falling into the singularity. Suddenly there's this white hole on the other side, and time no longer comes to an end.
Well, that's interesting. My crude understanding is almost like, okay, so you have these various light frequencies generated or frequencies generated when an atom jumps up, or an electron jumps to a higher level in an orbit. Is that something like that? Like it's quantum, babe. I don't know.
Yeah, it's not really related to that. I think the analogy that makes sense is with the Schrödinger cat, right? So there's this famous thought experiment where the cat is kind of dead and alive at the same time. And that illustrates the idea of a superposition. So that's very important, that basically a system can be in two states at the same time.
Right.
So what we need for this work is basically the fact that you can have a black hole and a white hole in a sense at the same time because of quantum theory. And depending on where you are in the evolution, you're more likely to see the black hole or you're more likely to see the white hole.
Probabilities.
But they're kind of always there. Yeah, exactly.
Okay.
That's right. Yeah.
All right. Well, it's very interesting. I guess time and space, or time, the universal properties of all systems is that, if you don't have exchange and transformation, then there's nothing, right? I mean, anyway, there's something in there that helps you get to this point of, it almost sounds like a wormhole, Is that another name for a wormhole? Black hole, white hole transition? Are we talking about a wormhole?
It's not really the same thing. I mean, there are some similarities. So the wormhole, the idea is that it connects kind of two different sectors of the universe, right? You can go through it and you enter some distant part of the universe. So that, in a sense, is similar here, because you would go through the black hole and you would come out of the white hole and you'd basically be in a different part of the universe. So that in that sense, it's similar. The differences are that it's just a one-way street. You can't go back, right? You can only go into the black hole and come out of the white hole. You can never go back into the white hole, right? Because the white hole, I guess we haven't really talked about this much. A white hole is basically the reverse of the black hole. So the white hole only spits out stuff, but nothing can actually go in, right? So in that sense, it's the opposite of the black hole. So that's what you would have on the other side. So once you've made that transition, that's it. You can't go back. I guess the other difference is that it would be a very violent way of traveling into the other part of the universe, because you still have to go through the black hole, right? So you'll still be pulled apart and spaghettified. So it's not really something that's very practical, I guess. Whereas with the wormhole, I guess the idea is that you survive kind of intact, more or less.
Okay. Well, it almost sounds like a white hole is the same thing as a Big Bang.
It's related. So they have a lot of things in common again. So they're both in general relativity, they're both described by singularities in the past, right? So that the black hole has a singularity in the future, where you fall in, eventually you hit the singularity. The Big Bang is a singularity in the past. It's the beginning of our universe. Everything just came into existence out of the singularity, right? And again, that's a puzzle. How do we make sense of that? And that's similar to the white hole. The white hole is also a singularity in the past. Everything just comes into existence basically out of nothing. So that's a similarity. The difference is that the white hole, of course, is very localized, right? It's not everywhere in space. It's just, in one particular point in the universe.
Okay.
Whereas the Big Bang, of course, is, everything all at once.
Well, it's very reminiscent, this black hole, white hole transition sort of duality speaks to the idea of parallel universes, maybe, multiverses, with all of this stuff going on. I don't know. I mean, it's not. Are we talking one universe here, and a black hole and a white hole are in the same universe? I mean, well, the other side of that transition, is that the same universe or parallel universes?
Yeah, so that's a great question. So I think so in the model we have, it actually looks like it's a separate universe. They're not really connected. I think this is a feature of this model. I mean, it's a simplified toy model. And one of the points is that the black hole that we have is basically an eternal black hole. So it doesn't get formed by any process, and it also doesn't disappear. It just sits there and eventually becomes a white hole through this quantum process. Whereas if you had a more realistic model, you would want the black hole to be formed, but the black hole could also disappear through a process called Hawking radiation. Black holes are actually supposed to evaporate and eventually disappear. And if you included that, that would change the picture completely, right? Because if you're imagining you have this black hole that's sitting there and it's kind of your window into the other universe, if you want to think of it like that, eventually the black hole disappears through Hawking radiation. You would expect these parts of the universe to be connected.
Yes.
And so then that would become the same universe, because then suddenly these things become connected. So this is more speculative. That's not something we see in our model, because our model is too simple, right? In our model, this is just a single process of the black hole going into a white hole.
How long does it take for a black hole to evaporate? I guess that is relative, I suppose, whether you're inside or outside, correct?
Yeah, absolutely. So it depends on what you mean by time, because time is relative to the observer, right? But yeah, you could define that question in terms of someone who's far away, who's looking at the black hole, and sort of seeing it very, very slowly evaporate. It takes very, very, very long. So for any realistic black hole, that's like, solar masses, or even the supermassive ones that you mentioned, it takes basically longer than the age of the universe, right? So this is a very, very, very slow process. But if you're asking, if you've got infinitely long to wait, eventually it will happen, right? So it is sort of something that would eventually happen if the universe kind of lasts forever, right?
Well, say you're inside. Okay, so you're an outside observer watching this, take place over billions of years. How about being inside a black hole? How long would it take if you were inside a black hole? And I'm kind of referring to time dilation, that kind of scheme, or that kind of, relativity. And reason why I asked that, I think I was watching the lecture by Carlo Gravelli, is that?
Yeah.
And he mentioned something of the fact that it feels like a few minutes if you're in the center of a black hole versus billions of years when you're on the outside. Is that an example of time dilation?
Yes, absolutely. That's right. So time is relative to the observer, and in strong gravitational fields, the effect is very strong. And of course, inside the black hole, or even just outside the black hole, if you're just staying outside, the effect is actually very, very dramatic. There's the movie Interstellar, where they actually use this, right? So the astronauts have to go to this planet that's just orbiting the supermassive black hole, and they just have a couple of hours or something for their mission. But that corresponds to like decades on Earth, just because of the very extreme time dilation, because the gravitational field is so strong.
Yeah. Let's bring in the dark horse, if we will. Where does dark energy fit into this?
Right. So that's kind of the missing piece, basically, right? So that's the key ingredient for this new work. So I mentioned that sort of in quantum mechanics, you're thinking about time evolution of systems. So this general property of quantum mechanics to tell you what is the future state of a system, how do you evolve it in time. For that, of course, you have to know what time is. You have to have some notion of time to define time evolution. And the issue is with general relativity, it's all relative to the observer. So there's different notions of time. So there's different notions of time evolution. So if you want to study your quantum theory, it helps if you have a good notion of time, if you have a clock that you can use. And that's true for many approaches to quantum gravity. You need some kind of reference clock that you trust in for your quantum theory. And the idea that we have is to use the dark energy for this. So dark energy is this kind of, you can think of it as the energy in the vacuum. So this is something that you can assume is there. You may or may not assume that it's there. The vacuum might have some energy or not. I mean, from a theoretical point of view, it's not so clear how to calculate that. But if you assume that the vacuum has some energy, then of course, because everything gravitates, right, it has an effect on, again, space-time and the universe. And at the moment, we observe our universe is expanding, and the expansion is actually accelerating. So we kind of need this dark energy to explain that. So it's actually something that we need even for cosmology to explain the universe. So I think it's pretty solid assumption to say that dark energy is somewhere in our description of the fundamental properties of the universe, and we probably need it. So our idea was to basically build a clock, if you wish, from that, because it's a form of energy. You can use that as a reference frame relative to which you define time. So in a sense, there's a preferred notion of time, which is basically the time experienced, if you wish, by the dark energy. So that's what we put into our theory.
So in a sense, dark energy is more than a fudge factor as we think of Einstein's cosmological constant. And the thing, so it has a particular vibration or cadence. Is that how you would compare that or cross-reference with time? Knowing, do you have to figure out what the vibrations or the rate of change, or I don't know, how is this? How does this factor in? How do you cross-reference with time? There must be some consistent clock mechanism going on there. Like an orbit, like quarks orbit.
Yeah, I see what you mean. Yeah, so it's a classical notion of time. Basically, I mean, whenever you have any form of matter or energy, there is, in a sense, a natural notion of time, which you can, in some sense, say is the time experienced by this particular form of matter or energy. So, for example, if you're looking at radiation, we're observing radiation from the early universe, like in the cosmic microwave background and so on. These are photons that travel at the speed of light, right? So they won't have a notion of time that is exactly the notion of time that we have in laboratory, sort of Earth-based systems. But they experience a notion of time that's called conformal time, which is basically associated to the fact that they always have to stay on the light cones. They have to travel at the speed of light. So if you're thinking about the equations, dynamical equations for radiation, for photons, typically you're thinking of conformal time. So we basically just push this a bit further and we apply this to the dark energy. And because that's, again, a different form of energy with different properties, it basically has its own time. I mean, I think about it quite mathematically, not necessarily in terms of atomic clocks or things like that, but it's something that's well defined in cosmology, that you can, for any type of matter or energy that's out there in the universe, basically you could define a clock.
And all of this time, dark energy, gravity, there's some sort of coalesce. Gravity, obviously, gravity does travel in waves, correct? Because of, what was it in 2015? What did they call that? LIGO?
Okay. That's right, yeah. We've actually measured the gravitational waves from these black hole merger events, which produce a lot of gravitational waves. That's right.
Okay. So now it's making a little bit of sense that ocean waves, they travel, but I guess you feel the force of the water. It's I don't know. We're going to have to think about that. So dark energy measure is used to measure time or define it, I suppose.
Absolutely.
So what is time? Time, space, that's kind of a, I've always kind of wondered about, the coin. If you take a coin, you've got a two-headed or a heads or tails. It's still a part of the same coin, time versus space. One can't exist without the other. So you have dark energy, and dark energy is cross-referenced to time. And so you have the relativity of time based on gravitation. Help me out here. Where am I? I'm lost.
Yeah, it's all very, very complicated. Basically, what we're looking for is like a universal standard of time, right? So something that doesn't depend on your local gravitational field, something that doesn't depend on what you're doing as an observer, whether you're traveling very fast or not, but something that applies to basically the universe as a whole, or any, large enough system in the universe. Basically, the thing that Einstein told us, in a sense, doesn't exist. There is no absolute time. We want to bring that back in here because it helps us in understanding quantum theory. Because for quantum theory, we have concepts of time evolution. So in that sense, it's a new proposal for introducing time back into quantum theory. And because the dark energy is everywhere, right? This is the energy of the vacuum. So it doesn't matter where you are in the universe. You would always measure this vacuum energy. It would always have the same value. So that gives you this kind of universal reference point that you can extract time from. That's kind of the idea.
Does it coalesce with the idea of the constant accumulation of dark energy as the universe ages? Let's say maybe at the time of the Big Bang, there is very little dark energy, and most of the universe was matter and energy we know, the matter we see. But now, what is it? The number's somewhere on the order of 60 to 70% dark energy in the universe. And so it's accumulated quite a bit. And as I understand, as scientists project, physicists, theoretical physicists project, is that, I don't know, maybe 5 billion years or 10 billion years from now, there'll be 99% or, some much larger number as far as dark energy goes. And at the end of it all, supposedly there'll be just complete dark energy.
Yeah. That's the simplest model and the one that fits best with observations. It might not be the correct one, but yeah, if that simplest model is correct, then that's indeed the future. Yes, because the universe expands, right? So everything else gets diluted, but the energy in the vacuum is just constant per, cubic meter or cubic feet or whatever. It's just going to be a constant value. So everything else kind of dissipates very slowly. And so the dark energy is going to be the only thing that survives. Yes, absolutely.
Is that what we think of? Is that the best way to think of dark energy, the energy of the vacuum?
I find that a very useful way of thinking about it. Yeah.
Okay.
It's if in cosmology, if you define the energy density of certain things, the energy density of galaxies and stars and other things. And generally, this is a complicated function of what the universe is actually doing and so on. The dark energy in the simplest manifestation you mentioned earlier is a so-called cosmological constant, which basically means it's a constant energy density that is always there, no matter where you are, no matter what kind of other objects are there. It's just a constant.
Very good.
And so, in a sense, you can think of it as a property of the vacuum, of empty space.
Well, what is the energy density of dark energy? Is there a concrete number?
Absolutely, yeah. You can look it up. So
numbers are cool. You got a lot of cool, crazy graphs in that paper, and I can't make heads or tails of them. But so where are we going with this? You have a number. You have a definite number for dark energy. So you can cross-reference that with time. Okay.
Yeah, exactly.
So we have a definite number for time that is unchanging, based regardless of whether you're in a vacuum or in the center of a black hole.
Exactly.
Well, that's very interesting.
So there's actually a way of thinking about this, which maybe helps further illustrating this idea of time. So if you think about what this time actually tells you, what this measures, it's basically the total space-time volume in your past. So you have to start from some initial point. Of course, you always have to have a reference point. What's time zero? So you put time zero at some point in the past. And then if you're asking what is the time at some later moment, you basically have to calculate the total space-time volume of the universe. So basically the volume of space times the time, you might think in normal units, that has passed, which gives you the space-time volume. And that's this new time that we have that is associated to the dark energy. So as the universe expands, of course, you have a lot more space than you had before. Time starts speeding up a lot because now you have all this volume. Whereas in the beginning of the universe, it would have been very, very slow.
Okay.
So that's the idea.
So does this lead us closer to a theory of everything, is in the sense of bringing quantum mechanics closer to general relativity?
So we would definitely hope so. I mean, at the moment, again, this is a simplified toy model, but it certainly suggests that, this dark energy time, gives you a good idea of how to combine quantum mechanics with general relativity, because that's often one of the biggest problems, understanding the role of time in this, supposed unified theory. So we have a proposal, which you could, in principle, push much further. You could apply that to any other system, because again, it's universal, right? The dark energy is always there. So this is always going to be a clock that you have, whether you want to describe the black hole or cosmology or some other system. So it's definitely a very interesting proposal. Of course, we have to study it a lot more and see if it makes sense in other contexts, or what it predicts, what it would tell us.
Okay, all right. So what's the bottom line? What is the bottom line? It sounds like we've got a time dark energy cross-reference, but wrap it up in a nutshell. What is, and what is this trying to say in a sentence or two? We've got black hole, white hole, chirality, if you will. We've got dark energy, and we've got time. Is there anything else? Is there anything else that we missed?
That's it. Yeah, it's about the question of whether time can end, or whether time just keeps evolving and changing your system into something else.
Okay.
And it's about the connection between black holes and white holes.
You're saying that time doesn't end. It can't end.
That's right. That's the proposal.
If it can't end, then how did it really begin in the first place?
That's exactly a great question. So the same thing would apply. Exactly. So if you're thinking about the Big Bang, you would have exactly the same question. How did the Big Bang suddenly come into existence? How did time suddenly begin? And again, if you follow this proposal, you would say, no, that's the wrong way of thinking about it. There must have been something before. There must have been a universe before that made, again, this kind of quantum transition through what we think of as the Big Bang. So that's exactly the logical consequence of this proposal.
I've heard of that term, big bounce. I'm not really sure what that means. Is that the black hole, white hole thing?
So the big bounce is usually used to replace the Big Bang. So it's exactly this idea that, you didn't have a universe that just came into existence and started expanding, but you had a previous universe that was actually contracting to some minimal size. Again, you might think of that as Planck scale or something like that. And then it makes that transition, starts expanding again. And that looks like it's the Big Bang. But it's not. It's not just the beginning. There was something before. So that's the idea of the big bounce. Now, in the black hole to white hole transition, it's a bit similar. Again, it's not the same thing, but there's a lot of similarities, because you would have some, massive concentration of energy, very strong gravitational forces, and eventually you have a transition into something new.
Is there anything else that you might add as far as beyond the wonder, why is this important?
Yeah, no, I mean, it's fascinating work. I mean, from my point of view, I'm interested in unification of gravity and quantum mechanics. And I see that as very promising, which I think is just from the theoretical point of view, just from the physics point of view, that's something we have to understand, how these theories actually work together. It could have an observational element to it as well, right? Because if white holes do exist in the universe because they're formed by this process, we might one day be able to observe them. So that would also be absolutely fascinating. So maybe, a few decades from now, you never know, there might be observational, insights into whether this makes sense or not.
So there are some ways that you can test parts of this, right?
If a white hole existed in the universe, that would be a very distinctive signature, right? Because it would be this object that stuff just keeps flying out of, which we have no idea what that would be if we saw that, right? So that would be a way.
A little better understanding of what you want to do is to really have a good definition of time that is constant. That is a good constant, and maybe if you have that constant, you'll be able to unify general relativity and quantum mechanics someday.
Mm-hmm. Exactly.
All right. Any closing thoughts?
Yeah, I mean, for me, these are the most fascinating questions. That's why I'm working on this stuff, and I hope other people find them interesting too.
I find it mind-boggling, fascinating, and exhilarating all at once. It's we're trying to do art and poetry. Science is art, and it's beautiful. Dr. Gillen, I want to thank you so much for coming on, and I'll keep an eye on you and see how your work is progressing, and I greatly appreciate it.
Thanks, Mike. Yeah, it was a real pleasure. Thank you.
Special thanks to my guest, Dr. Stephan Gillen, theoretical physicist at the University of Sheffield. Black holes transitioning into white holes, moving into the future, looking back into the past, space-time and energy swapping, the potential for dark energy as a reference point for an absolute measure of time as a constant, beginnings and endings, unification. Symmetry is the axis of duality, and everything flowing and spinning, creating countless swirls and eddied lines, the river of space-time to break on through to the other side. You have been tuned in to Weltanschauung, broadcasting from deep in the heart of the Petro Metro, aka Houston, Texas. I'm Mike DeLeonardis, and I have been bringing it to you. See you on the flip side.
We go